Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 7. One-Step Methods, Numerical Stability and Stiffness. It may be tempting to apply any of the numerical methods discussed so far with an arbitrary step size without much thought. But some of the numerical methods may not always behave as they should. Even in the absence of round-off or truncation errors, a numerical method, rather than dampening the numerical errors, could magnify them to a point where the errors continue to grow unboundedly. The numerical solution of an initial value problem with an unstable numerical method leads to unbounded growth with any choice of step size, whereas a stable numerical method does not cause numerical instabilities or unbounded growth. In some cases, the stability of a method may depend on the choice of step size. Such methods are referred to as conditionally stable methods. Consider the following first-order initial value problem, whose true solution is yx equals e to the lambda x. Applying the explicit Euler scheme gives, or for successive steps we obtain, where the term 1 plus h lambda is referred to as the amplification factor, and it will be denoted by xc. The amplification factor must be bounded to prevent the errors from growing. That is, absolute value of xc should be less than 1. For values greater than or equal to 1, numerical instabilities will be observed beyond a certain critical step size, i.e., h less than or equal to -2 over lambda, which is an upper bound for a stable solution. Applying the implicit Euler method to y prime equals lambda y gives, where xc equals 1 over 1 minus lambda h, which leads xc less than 1 for all lambda less than 0. The difference equation for the trapezoidal rule yields where for lambda less than 0, implicit Euler and trapezoidal methods are unconditionally stable. Runge-kutta methods are inherently conditionally stable because they are explicit methods. For example, for the RK2 with fx y equals lambda y, we may write then to get the current step, we write, or we can express it as follows. Xc is the amplification factor, as usual. Similarly, we can carry out stability analysis for higher-order runge-kutta methods. For RK2, the stability requirement leads to, or for real-valued lambdas, we get, for RK3 and RK4, we find the stability criteria as follows. The selection of the step size is important because the numerical method should be chosen such that it is not only accurate but also stable. Even though linearized schemes are unconditionally stable, in practice they may lead to some loss of total stability for nonlinear initial value problems. The conditional stability requirement can result in an extremely small step size for a large lambda. This phenomenon observed in initial value problems is referred to as stiffness. Stiffness depends on the initial value problem itself, the accuracy criterion, the length of the solution interval, and the absolute stability interval. Differential equations exhibit widely varying timescales. The components with large lambda decay very rapidly, while the components with small lambda decay very slowly. This creates numerical challenges, especially when trying to solve the ordinary differential equations with the standard methods. The rapidly varying component with large lambda dictates the use of very small step sizes over the entire solution interval to maintain stability. For lambda being a large positive number, e.g., lambda equals 10 to the 10, the solution to the following first-order initial value problem will decay very quickly. This initial value problem describes a rapidly changing behavior of y. When solved numerically, this initial value problem can be difficult to handle because we will need very small time steps to accurately capture the rapid decay, even though this solution is changing very slowly at later times. With this note, we conclude this lecture. That is all for now. See you next time with another topic. Bye.